All right, guys, back to problem 18. It says, the ropes seen are used to lower a 255 kilogram piano 5 meters from a second-story window to the ground. How much work is done by each of the 3 forces? So let's draw a diagram where we are showing our vectors. Okay? So I've got a 1,830 Newton force here. I've got a 1,295 Newton force here. And I have 2,500 Newton force of gravity. And we're starting here at y equals 5 meters, and we're going here to y equals 0. So our delta y, okay, points downward. Now, if this is a 60-degree angle, then 60 plus 90, this is 150 degrees. If this is a 45-degree angle, then 90 plus 45 is a 135-degree angle. So the work done by, I'll call this force 1 and call this one force 2, is going to be 1,830 newtons times 5 meters times the cosine of 150 degrees. So 1,830 times 5 times 150 cosine says that it's minus 7,924 joules of work. The work done by force 2 is going to be 1,295 newtons times the 5 meters times the cosine of 135 degrees. 5 times 1,295 times 135 cosine is a minus 4,579 joules. And did it ask us, oh, work done by gravity would be the mass of the, let's see, that was 2,500 newtons times 5 meters times the cosine of 0 degrees, which is 2,500 times 5. So 12,500 joules, and it's positive. Guys, if you were to add all of those up, what you essentially get is 0. Okay? Because all of the energy that gravity is essentially putting into it, the ropes are taking out. So this thing is going to move down at a constant speed. Okay? Which is what you want. You don't want to drop that piano. Now, want you to know that the force and the direction of travel, are perpendicular to each other, no work, okay? So, for a variable force, we're back to our integral. For a variable force, work equals the integral from S initial to S final of f of s ds, where f now is going to be a function in terms of location. work done would be equivalent to the area under the curve of the graph of the function f as a function of position. So let's look at problem 21 on page 228. Gotta hit the button. Okay, if we look at problem 21 here, it says a 500-gram particle moves along the x-axis and experiences the force as shown. Okay, the particle's velocity is 2 meters per second at x equals 0. What is its velocity at 3 meters per second? Well, the first thing that we need to do is we need to get the area under the curve. So between 0 and 1 meters, it's experiencing a constant force. Okay, so the area under there is 15 times 1, so it's going to be 15 joules. Between 1 and 3, it experiences a variable force, but I've got a triangle, so it's 1/2 the base times the height. So 15 times 2 divided by 2, that's also 15. So this object experiences 30 joules of work being done on it. Okay? So let's give ourselves a little working room here. So I've got work equaling 30 joules, which has to equal 1/2 m v final squared minus v initial squared, because work equals change in kinetic energy. So 30 joules is equal to 1/2 times 0.500 kilograms times v final squared minus v initial squared, which was 2 meters per second. So 30 times 2 divided by 0.5. That's 120. And joules divided by kilograms gives me meters squared over second squared, is going to be equal to v final squared minus 2 meters per second squared. So 2 squared is 4, 120 plus 4. Take the square root of that. V final is 11.1 meters per second. That's how fast it's going at 3 meters. Okay, see where everything came from? All right, so that's kind of looking at it graphically. Now, the one variable force that we're going to encounter, okay, on a regular basis is a force I've already mentioned, and that's the spring force. So let's talk about the spring force for a moment. We know that a spring force from a spring, is equal to minus kx. So if I look at work equals the integral from S initial to S final f ds, for a spring, we could say work from x initial to x final is the integral from x initial to x final of minus kx dx. Okay? Now k is a constant. It's of course going to factor out. I jumped too fast. Sorry, guys. And when we take the integral, the work from the spring is equal to the negative of 1/2 kx final squared minus 1/2 kx initial squared. So the work from the spring is the negative of the change in spring potential energy. Now remember, we're setting our equilibrium position at x equals 0. And notice the work done by a conservative force, the spring force, like gravity, okay? The gravitational potential, change in gravitational potential energy, change in spring potential energy causes a change in kinetic energy, which is always going to be the opposite, the change in potential energy. Okay? We know that work done by any force is equal to change in kinetic energy, and it's equal to the negative of the change in in potential energy if we're dealing with a conservative force. Guys, this just kind of reinforces some things we've already talked about, but let me kind of remind you. Work done by any force is equal to change in kinetic energy, okay? Work done by gravity is negative the change in gravitational potential energy, which equals the change in kinetic energy. Work done by a spring is equal to the negative of the change in spring potential energy, which is equal to the change in kinetic energy. We know that kinetic energy is 1/2 mv squared. We know that gravitational potential energy is mgy. We know that spring potential energy is calculated as 1/2 kx squared. Okay, and what this gets back to is that kinetic energy initially plus spring potential energy initially plus gravitational potential energy initially equals kinetic final plus spring final plus gravitational final. Now, if you wanted to, kind of play with things, you can have then U spring initial minus U spring final plus UG initial minus UG final equals K final minus K initial. Okay, this is the negative of change in spring potential energy. And this is the negative of change in gravitational potential energy. And it equals the change in kinetic energy. Okay, just a little bit added on. Now, when we talk about non-conservative forces, a non-conservative force could be an external force, one from outside the system, like a push or a pull. Okay? An external force is going to change the energy of our system. It's going to change the total energy of our system. So work external equals the change in internal energy of the system. So energy final is going to be energy initial plus the change in energy of the system. So that we could say energy final equals energy initial plus work external, which means I have work external plus kinetic energy initially plus our potential energy initially has to equal kinetic final plus potential final. Okay? Now, we have also another kind of non-conservative force to talk about. And this non-conservative force is a dissipative force. A dissipative force is called a dissipated force because it dissipates or decreases your amount of mechanical energy. Okay? It is always a non-conservative force, and what it's going to do is it's going to take our mechanical energy and it's going to turn it to thermal energy. It's still going to be inside the system, but it's now put that energy in a non-useful form for doing work. Okay? That's going to be important to us next semester. So, friction is a non-conservative dissipative force. Work done by friction is always minus F delta S because the angle between the direction that friction points and the direction of travel is always 180 degrees. So we're always taking the cosine of 180, so it's just minus F delta S. And the change in thermal energy of the system is minus the work done by friction, so it's always equal to F delta S. So what we can say is that work external plus kinetic energy initially plus gravitational or spring potential energy initially has to equal kinetic energy final plus our potential energy final plus any change in thermal energy. Okay? So you can think, this is what I start with, this is what I end with. Let's look at problem 32 on page 229 in the textbook. So let's get to problem 29. Okay. Says a 5 kilogram mass hanging from a spring scale is slowly lowered onto a vertical spring as shown. What does the spring scale read just before the mass touches the lower spring? And the scale reads 20 newtons when the lower spring has been compressed 2 centimeters. What is the value of the spring constant of the lower spring? To what compression will the spring read? Now this one doesn't have any friction in it. We're just going to kind of do a before and after. Well, I don't think I want to do that one. Let's skip that one. That one's just kind of not very fun. Let's see. Let's look at problem 32. I like 32 better for what we're trying to do. Okay, it says a 55 kilogram softball player slides into second base and generates 950 joules of thermal energy. It says, how fast was she running? Okay? So let's think about this. Our kinetic energy initially is 1/2 times the mass of our softball player, which is 55 kilograms, V initial squared. Our gravitational potential energy is 0. Our spring potential energy initially is 0. Okay? And that's what we have to begin with. Now, all of that kinetic energy is going to end up going to, so I have kinetic energy initially, I have G initially, we have U spring initial, that has to equal kinetic final plus UG final plus spring final plus delta E thermal. Well, I have 1/2 times 55.0 kilograms V initial squared plus 0 has to equal 0 plus 0 plus 0 plus our thermal energy, 950 joules. So if I solve this, 950 times 2 divided by 55, take the square root of that, I get the speed initially to be 5.88 meters per second. Okay? they experienced a dissipative force. So, not bad. 32 was the one I originally picked out anyway. All right, now, let's look at problem 54. And then we're going to talk about power. Okay, so we're going to flip over here. I'm going to look at problem 54. I'm going to flip a page. What's the one I originally wanted? No, 54 is not the one I want. Let me see, what's the problem that I want? Well, I'll look at the problem later. Okay? So, let's skip problem 54. It's not the original problem that I wanted. And let's talk about power. Okay, let's see how I'm doing here on disk space. Okay, we're still good. So, let's talk about power. We're going to use P as our symbol for power, and power is delta E of the system, the change in energy of the system with time. Or you can think about it as the rate of doing work, because it takes work from external source to change the energy of the system. So if we were to look at page 224 in the textbook, okay, it goes through and it says work, you know, the dW is equal to F dot dr. So the rate of change of work is force times the distance moved for a constant force. What you can get from that, working through, is that we can also calculate power as force times velocity times the cosine of theta. Okay? So there's another way to calculate force. So we're going to do a simple problem here. Force problems are usually pretty easy. We're going to look at problem 36 on page 229. Okay, so 36 on page 229. Is that one? Yeah. All right. Let's look at problem 36. Okay. It says, how much work does an elevator motor do to lift a 1,000 kilogram elevator to a height of 100 meters? How much power must the elevator supply to do this in 50 seconds? Okay? Now, if you think about the elevator is having to lift against gravity. So, work external is going to equal change in gravitational potential energy. Okay? So it's going to be the so our work external is going to be the mass of the elevator, which was given to us as 1,000 kilograms. And 9.80 meters per second squared, and our change in height, our delta Y, is given as 100 meters. Okay? Because it comes to a stop. All of the energy that the motor put in ends up in gravitational potential energy. We're assuming no friction. So 1,000 times 9.8 times 100 says that the work external is 9.80 times 10 to the 5 joules. Now, the power is going to be the amount of energy that was delivered divided by the time that it was delivered in, and it was delivered in 50 seconds. So that's 1.96 times 10 to the 4 joules per second. Now, a joule per second is called a watt. So we could say this is 1.96 times 10 to the 4 watts. So the rating on a light bulb is the amount of energy that it's dissipating per second. So if you have a 50-watt light bulb, it's dissipating 50 joules of energy a second. It's converting them into heat and light. Okay? Now, another problem for us to look at, to think about power, let's see. It's problem 40. It says a 50-kilogram sprinter starts from rest and runs 50 meters in 7 seconds at constant acceleration. What is the magnitude of the horizontal force acting on the sprinter, and what is the sprinter's power at 2 seconds, 4 seconds, and 6 seconds? Okay, so we've got our sprinter, and the mass of our sprinter is given to us as 50 kilograms. Okay, and they're running, starting from rest. V initial at t equals 0 is 0. And they cover 60 minutes. They cover 50 meters in 7 seconds. Okay? All right, and we know that acceleration is constant, which means our force is constant. Now, I can use the distance and the time and the velocity initially being 0. Let's see if we can't get our acceleration. No, let's see. Velocity initially, I've got the distance covered, I've got the time. We told anything else? Nope. That's it. So I know that x final equals x initial plus v initial x delta t plus 1/2 a delta t squared. So I've got 50 meters has to equal 0 plus 0 delta t plus 1/2 a times 7 seconds squared. So 50 times 2 divided by 7 squared says that our acceleration is 2.04 meters per second. I had to use our motion equation to figure out excuse me, acceleration. Now, I've got my acceleration. The problem asks me how much power, what's the magnitude of the horizontal force acting on her? So, sum of the forces in the x direction has to equal mass times acceleration. So force x is going to be 50 kilograms times 2.04 meters per second squared. So we've essentially got 50 times 2.04, 103 Newton force. So she's moving this way, okay? So X initial, X final, and our force is this way. They're parallel. Now, the next thing it asks us is, what is her power output at 2 seconds, 4 seconds, and 8 seconds? So, if I use this equation, I see. I can use a couple of things. We know that power is that the rate of energy dissipation with time, okay? And it could be calculated as delta E over change in energy over change in time. Come on, scroll down. I'm scrolling the wrong way. Sorry guys, I'm trying to make sure I write the exact right, easiest way equation for you to get where you need to get. So we could use F times V times cosine of theta, but that's not going to do us any good. We essentially need to figure out how much energy has been dissipated at 2 seconds, 4 seconds, and 7 seconds. So if we were to look at our force being constant, okay, over that distance, then the work done should be the area under the curve. Now we know our force is 103 newtons, and I got to figure out the distance. So if I go back to my motion equation, at t equals 2 seconds, then I can say that x is equal to 0 plus 0 delta t plus 1/2 times 2.04 meters per second times 2 seconds squared. So I have 2 squared times 2.04 divided by 2. I get at 2 seconds my x to be 26.1 meters. So 26.1 meters times 103 newtons. Our work done by this point is 2,692 joules. So our power is going to be 2,692 joules divided by 2 seconds. So I've got a power rating of 1,346 joules per second. And you could do the same thing with 3 seconds, 4 seconds, 5 seconds, so on and so forth. So you just have to calculate the area inside that rectangle, okay, force over distance, and then divide it by the time. So it's not hard. I just wanted to kind of think it through for a second. Now I have a couple more problems listed here. I will probably just include those in the packet, because 41, let's see. Yeah, it's a very similar problem. And then 43 and 49. Let me look at 43. Oh, 49 is right there. Yeah, 43 and 49. I'll just include those in the packet. Okay? It starts to get very repetitive. All right. Now, we bounce to chapter 10 and look at problem 73. It's the last problem I want us to look at, and we will be done with chapters 9 and 10. So if I look at problem 73, I haven't worked this one yet this time around. I'll include that in the packet, okay? This ends chapter 9 and 10. So 9 and 10 are nice and wrapped up, and yay, we're well on our way to test 3. So next chapter will be chapter 11.